So now we want to prove this shortcut lemma. And first, if G has degree 0, then this is vacuously true, trivial. So we can assume that it has, positive even degree. So let U be a fixed neighbor of G, and let B prime be the vertices other than G, and let G prime be the UV shortcut of G for some choice of B. And now what we need to check is that we need to check the, for this G prime, for vertex set, we want to check that this is at least T. The number of edges leaving vertex set X is, at least T. So we need to check. So we want, say, check this holds for all, say, X is a non-empty proper subset of B prime. Because, we have to check two cases, whether X is a subset of B prime or X contains this vertex G. But they are complement each other. So if this holds for all such X, then we consider the complement. Then that's naturally, covers all vertex set which contains G. So it suffices to only check that, check for this. And then let's consider how does it changes, on this shortcut operation. So we have G and U and B, and we know that G is not in X. And previously, this was the graph, but now this is the graph. So if X contains both U and V, then it might lose two edges, 1, 2, which is leaving X. And if it doesn't contain any U and B, then number of edges leaving is same. So for that, we don't really have to worry about. And if it contains one of U and V, then it loses one edge leaving X, and it gains one edge leaving X. So previously, delta G X was at least T. Then again, in delta G prime, the number of edges leaving X is again T. So also this case, we don't have to really worry about this. So this blue graph, blue vertex set is the one that's possibly dangerous. So let X be a non-empty proper subset of B prime, and consider a vertex V, which is neighbor of G but not U. Among the edges leaving X, the UV shortcut operation destroys UG or PG if X contains u or v, and it adds uv if x contains exactly one of u, v. So thus the shortcut operation make x fail to satisfy this only if u, v are all in x and the number of edges leaving x is at most t plus 1. If this was more than t plus 2 at the beginning, then even if you lose 2, it is still at least t, so it is okay. So even at the beginning, it's either t or t plus 1. And then it loses 2 because u and v are all in x. That's the only possible cases which can yield the, is the number of edges leaving x is strictly smaller than t. So we call a set x dangerous if x is a non-empty proper subset of P prime that contains U and satisfies this, the number of edges leaving x is less than or equal to t plus 1. In this case, so now recall our goal. Our goal is when we have u and g, and among the neighbors, we want to find the v. So v is not fixed. U is fixed, but v is still our hypothetical choice. We want to choose such a thing so that there are no x which contains both of them and satisfy this. So what we want to find is we want to find the vertex v which does not belong to any dangerous set. So that's exactly what we want to find. So a UV shortcut of G is, say, T edge connected relative to G if and only if all dangerous set say omit V. So let M be the union of all dangerous set. And now what we want to prove is that M itself is dangerous and it omits at least one neighbor of G. Then this is sufficient for our purpose. All we have to do is we take that was some specific neighbor which is not in the union of all dangerous sets. So it is not in any dangerous set. So we take that V. Then UV shortcut of G is also TH connected relative to G. So first, let's show that M itself is dangerous. For that, what we want to do is we want to that if X and Y are dangerous, its union is also dangerous. So we want to first prove that this holds. So we have X and Y. And if one is inside the other, then this statement itself is trivial. So we assume that both x minus y is not empty and y minus x is not empty. So we want to first prove that because every time, it's dangerous, then we already assume that the original graph G is TH connected relative to G. So for the original graph G, the delta is always at least T. And then dangerous set have delta value at most T minus 1. So it's out of two values. So we know that T is an even number. So once we know something's parity, then it automatically determines which of T or T plus 1 it is. So we want to first prove that the X union Y, so this delta is for G. If we don't write anything, this is for G. The number of edges leaving X union Y is odd. And we know that X, Y are dangerous. So delta X and delta Y are all at most T plus 1. And by the definition of dangerous, we know that G is outside here, and U is in both X and Y. And what do we know? So we know that if we add these two, 2t plus 2 is at least delta X plus delta Y. And we know that this counts all the edges of this and this twice, this once, this twice. So this expression counts all the edges of this type, and some of them twice. And what does this counts then? This counts, this edge, and this edge, and this edge. And these type of edges are not counted. So we can add that, which is say 2 times the number of edges in the edge cut. But U is here and G is here. So this is at least 1. So here we have delta X minus Y plus delta Y minus X plus 2. But what do we know? These are at least T, because the original graph is TH connected relative to G. So we have 2T plus T. So that means every one of inequality must be all equality. So what do we get? Delta X equal delta Y equal T plus 1. Delta X minus Y equal delta Y minus X equal T. Then what do we know? This delta X union Y is counting these edges, where say delta Y plus delta X minus Y, delta Y counts, so this is Y, this is X, this edge and this edge, and this edge, and delta x minus y counts this edge and this edge. So give me a moment. If we have a let me check. Yeah, let me write it again. Sorry. So let's just say we have a two set y and x minus y. And in the left hand side, it counts all the edges of, say, this type. And here it counts all the edges of this type and this type. And this type and this type. So on the left hand side, it counts all the black one. On the right hand side, it counts all the, red and blue edges. This red blue edges, counts the same edge set, twice. So if we just consider about parity, these two expression has the same parity. And what did we just show? This is t plus 1 and this is t. So this is odd number. So this is odd. And also from this we can conclude the parity of the intersection of x and y. And because this is odd and the entire thing is even, so we first know that this union is not entire thing. And also the, what do we know? Intersection plus x minus y at because of the same logic here. It has same parity as delta x. So again, x minus y here is t. And this is t plus 1, so this is odd. So now we are close to prove that x union y are, dangerous. So what do we know? We know that if we take intersection and union and add, then those two are both odd number and at least t plus t. Each of them are at least t. And we know that this is at most delta x plus delta y. Again, by the same logic as here. So all of these are, again, you can check that this inequality holds. And then you know that this is at most 2t plus 2. So it's 2t, and here 2t plus 2. And we know that both of them are odd number. Then the only possible, possibility is that both of them are t plus 1. So x union y is dangerous. And conclude that M is dangerous. So now we want to show that there exists some vertex which M omits. So if no sets are dangerous, then you can choose any V. Then UV shortcut of G works. So we may assume M is not empty set. Also, what do you know? M is a proper subset. We show that however many times you take the union, then you never get the entire V prime. So this is a proper subset of V prime. And we know that G is TH connected relative to G. So the number of edges leaving V prime minus M is at least T. So we have M, we have V prime minus M, we have G. So if M contains all neighbors of G, then what happened? All neighbors are going here. Then the number of edges leaving M union G is the number of edges leaving M minus the number of edges to G. So delta of M counts all these edges, but now it only counts these edges. And since we know that this dg is a positive even number, at least 2, and M is dangerous. So what do we know? We know that there are at least T edges leaving this set, and that's same as its complement. The number of edges leaving its complement, and which is delta of M minus dg, which is G is at least 2, which is so at most delta of M minus 2, and then delta of M is at most T plus 1, so this is at least at most T minus 1. This is a contradiction. So this contradiction implies that this M omits some B, which is neighbor of G, and UV shortcut of G is TH connected relative to G. So this proves the lemma. So now what we want to do is we want to, as plotted before, we want to apply this shortcut operation and then apply induction at the end when this vertex G becomes isolated vertex. For that, one more thing is necessary, so that this vertex has to have an even degree. So we have to be able to find the vertex with even degree so that we can keep do this. Otherwise, at the end there is one edge. This operation does not really, give you. And in this shortcut lemma, also G is a vertex of even degree. So for that, we need to prove this. Obviously, there could be a graph with all vertices have the even degree. So not just any graph, but the we need to be able to find some graph to which we can reduce the problem. So we can actually show this memory minimally TH connected multigraph has a vertex of degree t. Here, minimally TH connected multigraph means that once you delete edges, it is no longer TH connected. So one thing more we can do on this proof is that if this graph is not minimally TH connected, then we delete some edges until it becomes minimally TH connected. And then once you deleted it, the remaining graph, if we find the orientation on the remaining graph, then we add these edges back, and then we orient this in arbitrary way. Once you already have a K edge connected orientation, and you add some edges and arbitrarily orienting the added edges doesn't hurt the edge connectivity. So, we can actually, assume the original graph to be minimally 2K edge connected. And here, T will be the 2K later, so this will be the vertex with even degree that we will use later. So let's prove this lemma in the next video.